Continue with the last speaker of the day, Corwin, who is going to talk, well, from Columbia University, who is going to talk about dynamic.
Right, well, thank you very much. It's a pleasure to be here. I've never been to Cambridge before, so it's great to be here. Unfortunately, I'm only here for a day, so I'll need to come back. So I really liked kind of the spirit of the talk so far today. You know, a lot of kind of looking forward and some speculation. So I'm going to do something similar. The question, kind of the broad question that I'm interested in this talk is how do you describe interface growth models that have a preferred height? So, you know, we're used to models that just kind of grow and grow and grow, or kind of oscillate up and down, but we want to think of imposing some sort of potential so that the height function prefers a certain level. And then the question is, what are some natural continuum equations and then natural discrete equations, and how do you get from one to the other? So I'm not going to answer all these questions, but let's anyway start grand and then do something much more modest. So in the spirit of what Martin was talking about earlier today, we'll consider a sort of generalized KPZ equation. And I won't write quite all, you know, as many symbols, a 54-dimensional space of them or whatnot. But let's imagine a one-dimensional height function, and we have our usual sort of terms. And now if we want to impose that there's some sort of preferred height function, we could imagine different mechanisms. So one would be to have some sort of potential that just compresses us. So for instance, if f of h was just linear, h, this would certainly suffice. Then we could imagine having a term that sits in front of the nonlinearity. And then there's the space-time white noise. And we could also throw in some other terms. So for the moment, if you forget about the nonlinearity, this becomes a sort of generalized space-time Ornstein-Uhlenbeck process. And you can imagine some conditions on f, for instance, that f is the derivative of a potential that grows to infinity. And then this would have some preferred height function, and you would kind of oscillate around that. Now, it's a little less obvious what characterization one wants of G to have a similar sort of property. Let's forget f for the moment. If G is just plus 1, okay, then actually there's an overall drift of minus t over 24. This is something that you get out of the formulas. And if it's a minus sign, then it's an overall growth of t over 24. So you might imagine a G which, when h gets large, becomes positive, so you have a negative drift, and when h gets negative, becomes negative, and you get a positive drift. Okay, so I could imagine this is some sort of equation of this sort. Now, ultimately, I'd like to show that some discrete models converge to this, but I'm not going to do that. I'm going to forget about the nonlinearity in this talk, and we're going to deal with the linearized equation, the Ornstein-Uhlenbeck process. And so the idea of the talk is I'll introduce a discrete growth process, which is called the dynamic ASEP. And the first half of the talk is going to just discuss properties of this dynamic ASEP model. Alone, it's an interesting model. It has interesting algebraic properties, connections to sort of integral probability, and I'll espouse a little bit about those with an eye ultimately towards taking these scaling limits. And that's what I'll do. And the second part of the talk is the scaling. And I'm going to take what can be called a very weakly asymmetric scaling limit, which brings us to Ornstein-Uhlenbeck, the space-time Ornstein-Uhlenbeck process. One would hope to have a weakly asymmetric in the spirit of Bertini-Giacomine limit, though, as I'll talk about in a little while, it's not so clear exactly how that's going to work. And we'll do this both in the case of the line, so the full line, and then actually in a more generalized version of the model, we'll do it on the torus. Okay, so what is, let me just say, so this is, the first part is from joint work with Borodin that we published last year. And then this second part is joint work in progress that should be out pretty soon with my grad student Konstantin, Promit Ghosal, and then Konstantin Matetski. Okay, so let's start. Okay, so what is dynamic ASEP? We'll just abbreviate it as DASEP. So it's a very simple growth process, And unlike the usual ASEP, where you can kind of interchangeably think of it as a particle process or a growth process, it's much more natural to only think of this as a growth process. So the state space is going to be denoted as a vector S, which will be a set of heights Sx for x and z. And we'll assume what's called the SOS, the surface-on-surface condition, which says that S of x minus S of x minus 1 is either minus 1 or plus 1. So in other words, you have a bona fide height function that has up and down increments of this sort. Okay? So the usual sort of picture. So the dynamics are going to be the following. So imagine that you have maybe I'll draw the other one first. So imagine that you have a local maximum, which has height s. That can become a local minimum, and it will do so at a certain rate. And vice versa, if you have a local minimum of height s, that can become a local maximum at a prescribed rate. And so I'll write down the specific rates. They're going to depend on two parameters. So they'll depend on a parameter q, which will be in 0, 1, and a parameter alpha, which is anything between 0 and infinity. So the rate of the drop is the following. And the exact formula is going to be important for the first part of the talk, but not as much for the second. Okay, and the second formula is this. Okay, so let's not focus so much on the details of the formula, but rather what is it saying. Okay, and I should say that, so this model was introduced by Borodin. It came out of a certain algebraic machinery using elliptic quantum groups and the Yang-Baxter equation for that. Okay, so what is this saying? So what it really is saying is that you have some sort of height profile. So I'll measure s in the vertical direction, and let's say eventually it's somewhere low. Now whenever it is above the height of log base q of alpha, when it gets very high relative to this log base q of alpha height, then the probability of going up versus going down, assuming that you can, shifts so that it becomes roughly probability or rate q of going up and rate 1 of going down. So that's when you're very high. It's approximately this. When you're very low, it's the opposite. So it's rate 1 of going up and rate q of going down. And right when you're at this level of s equals log base q of alpha, these two rates actually equilibrate. They're the same, and you get something which is like 2q over 1 plus q. So this is the rate of going up and down. So the overall effect is that when you're high, you want to go low, and when you're low, you want to go high, and everything is equilibrated to this level of log base q of alpha. In some sense, you can actually just kill the alpha from this by centering everything by this log base q of alpha. It does make sense to have the alpha, because if you take alpha in these formulas to 0 or infinity, you kind of move your reference frame way down or way up, then you just recover the standard ASEP model. Okay? Once you've kind of moved it all the way down to minus infinity or plus infinity, you just see 1q, or q1. Okay? Okay, so this is the model, and the kind of basic question is, how does the nature of this model differ from the nature of the standard ASEP model? In standard ASEP, you have these nice results about fluctuations going to the KPC fixed point, or if you take weakly asymmetric limits, you have limits to different stochastic PDEs, you have exact formulas, all of this sort of story. How does this go through? So that's what we'll explore. So the first sort of exact property of this model, which I'm going to describe, which will actually be very useful in the subsequent section as well, is about the duality, the Markov duality that's enjoyed by this process. Okay, so it turns out that there is a nice relationship between this dynamic ASEP and the standard ASEP. So in order to do this, I need to just introduce the generators of the two processes. So let's call Q alpha, let's call this the generator of the dynamic ASEP. Call it d ASEP. acting on functions of heights. Okay, so this will act on a function of the entire height. And then we have the generator of the standard ASEP with n particles. So let's say n is any integer bigger than or equal to 1. So this is just the generator in terms of particles, so of the standard ASEP acting on functions of particle locations. So maybe I'll denote it as x vec. So x1 bigger than up to xn in Zn. Okay. With left and right rates LR. Okay, so the usual picture, you have particles, and some holes, and you jump left and right with these rates. Okay, so n is an arbitrary number, so say it's 3, and up to 3. Okay, so the duality it's a standard sort of Markov duality statement, which says that you have two Markov generators, and you're going to have an operator, or you're going to have a functional that will intertwine the two. Okay. So I need to define the functional for you. So here's the duality functional. So for every n, and then you have q and alpha. So it takes as its argument the state space of dynamic ASEP and the state space of a n particle standard ASEP. And it's a little bit more complicated than the usual duality that one has for ASEP, which I'll remind you of in a second, but it's not so much more complicated. Okay. So there's some kind of simple factors. And then the term that really encapsulates the behavior is this last one, what I'll call f alpha of s xk. Okay, so what is this f alpha? So f alpha of s is defined as q to the minus s over 2, alpha to the 1/2, minus q to the s over 2, alpha to the minus 1/2. So it's some map of an integer, height, s, onto this sort of quadratic lattice. Okay, so you're exponentiating q to the s, and then q to the minus s, and then making some combination of the two. So the statement of the theorem is the following. It says that if you apply the generator of dynamic ASEP to this functional acting in the s variables, so it acts here, that's the same as applying the generator of the standard ASEP with parameters 1 and q, and for any n, to this same duality functional, now acting in the x variables. In other terms, what it means is that if you look at the expected value of this functional and you run either the s process or the x process, you can't tell the difference. In expectation, it will have the same effect on the evolution of this expectation. Okay. Okay. So, why is this sort of let's take a step back. What does this say for the standard ASEP, right? Because we said that there is a limit of dynamic ASEP that recovers standard ASEP. So if you take, for instance, alpha going to 0. In that case, the duality functional simplifies considerably. I think you get something like, so this is alpha going to 0, and you get that the duality functional becomes like a product of q to the k minus 1, and then you get these s xk minus xk over 2. So this is the case of alpha goes to 0. This type of duality is something that's familiar in the context of standard ASEP. This exact form is new, but one has dualities, for instance, ones that were proved by Borodin, Sasimoto, and myself, of this form for a standard ASEP. And this has been a useful tool in lots of computations and also in some stochastic analysis. So, what I'll explain is a few applications of this duality. First of all, in terms of kind of how do you compute formulas for this dynamic ASEP, how do you get formulas? And the second is how do you use this duality, which seems rather complicated, to prove a stochastic PDE limit. Okay. So let's just record a quick corollary of the duality. If you remember what it means to apply generators, what this tells you is that if I define a function u, say tx, to just be the expected value of my duality functional along the trajectory of s, so I look at s at time t, and then evaluate the function at x, then u will satisfy a differential equation, which is the generator applied to u, but the generator of the x variable. Right, is this clear? Because when you differentiate, you bring that in the expectation, it produces the generator of the Markov process, but by the duality, you can interchange that with this generator. And then you can pull that out of the expectation, and you get this equation. So here's the sort of cool thing about this duality. This, in principle, the dynamic ASEP really depends on alpha and q, as does the duality functional. But the right-hand side generator doesn't depend on alpha. This is just the standard ASEP, and there's a very well-developed Fourier theory for how to diagonalize this the standard ASEP, the n-particle standard ASEP generator. So if you can compute the initial data, then you can always write down integral formulas in the spirit of Fourier analysis for the solution at time t. So in a sense, for free, you get formulas for this expectation out of just knowing how to compute formulas for standard ASEP. The one particle case, just for illustration, is very simple. Then you're dealing with a sort of asymmetric, one particle random walk, and you can of course use regular Fourier series for that. Once you have multiple particles, then it gets a little bit more complicated. But this is a theory that we've developed over the last few years.
Can I have a very naive question?
Yep.
What is this L in your original general standard? Somehow you had L, and now you change it into.
Oh yeah, no. So I'm thinking, initially L and R represent the left and right rates, and now I'm specializing them to be 1 and q. So this is just defining the notation. Now I'm specifying the values. Okay. Now, it's not necessarily the case that it's actually so easy to compute the initial data, right? If I plug in some specific height function and I try to evaluate this, maybe the height function is deterministic, maybe it's random, but it's kind of a complicated object, and you really want something more compact if you're going to solve this differential equation. So what I want to explain is that there are a few initial data, at least a few I know of, for which we can actually compute quite concisely what the evaluation of this u at time 0 is. And in the process of doing that, we're going to come across some kind of nice connections to q orthogonal polynomials, and eventually to the stationary measures for this process that will guide us in our exploits to finding a scaling limit. When we started, we didn't actually know what the scaling limit should be, but we knew something about the scaling limit, and that comes from this calculation that I'll show you. Okay, so what are some natural initial data for the dynamic ASEP? Well, one knows, if you've seen anything about ASEP, that the wedge or the step is kind of a very natural one that people consider. So this means to take at time 0 just absolute value of x, right? So your height function looks like what Christoph was drawing in his previous talk. Now, for this initial data, it actually turns out, it's not a very complicated calculation, but it turns out that you can evaluate what this u at time 0 x is equal to. And it has a fairly compact form, so it's some product. I'll write it as what's called a q symbol. I'll remind you very briefly, so if I write a q n, it's not going to really matter, but it's equal to the product of 1 minus a, 1 minus qa, all the way up to 1 minus q to the n minus 1a. Okay. So anyway, so it's just some product. And then which does depend on alpha. But the cool thing is that the dependence on alpha and the dependence on x separate. So you get, and this is just a simple evaluation, k less than or equal to 0 minus q to the k minus 1. So there's some constant that depends on alpha, and everything else, the x, is completely independent. So up to the constant, this is independent of alpha. Which means actually not only can you use the diagonalization of the generator of standard ASEP, you can actually use already the formulas that are known for standard ASEP because, well, up to this constant, the right-hand side doesn't even depend on alpha. Okay, but this is not so hard to see. What's a more interesting calculation is what's called half-stationary initial data. And this required a little bit of ingenuity to come up with what this should be. So what does half-stationary mean? On the one hand side, it's going to look like the wedge, and on the other hand, it's going to look random. So for x bigger than or equal to 1, we said Sx equals to x, so just like on the right-hand side here. But for x less than or equal to 0, assume that you're given the value of Sx, then you choose Sx minus 1 according to the following Markov chain. So we set Sx minus 1 equal to the value of Sx, and then either we add 1 to it or we subtract 1 to it, and we do that with probability, complementary probabilities. So on the one hand, it's q to the Sx over alpha plus q to the Sx. In the other case, it's the opposite. Again, alpha somehow is inconsequential. You can kind of center it away. So but it's of the form q to the height over 1 plus q to the height, and the opposite. Now, so you know the picture is you have this, and then when you get to 1, you start to take some random walk. Now, what are the properties of this random walk? When the height gets large, the probability of increasing gets small, and when the height gets small, very negative, the probability of decreasing gets small. So this random walk is some sort of discrete version of an Ornstein-Uhlenbeck process. It has a mean reversion mechanism, so it doesn't like going too high or doesn't like going too low. For use in just a moment, let me just write down the generator acting on a function. So it's just the probability of going up, and then Sx plus 1, and the probability of going down. Okay. So for this half-stationary initial data, it turns out actually that we can also compute the value of u at time 0. And if I call the thing, this product, if I call this star, then this is actually equal to, up to, again, a constant. It's equal to star, but with the replacement of xk by xk minus 1. Okay, so it's a very minor modification of the same formula. This is a much harder thing to prove, right? Because you're looking at the expected value, but the initial data is random. And you have a rather complicated observable, so you basically need to march along using this K Markov chain, evaluating the observable, and trying to somehow use properties of K and the observable to give you a way of doing this. So I'm not going to give you a proof, but I want to explain to you the kind of key property of this half-stationary Markov chain, and which will eventually lead us to something that we'll use, which is the stationary initial data. So how should I think of K? Well, as I said, K is a discretization of an Ornstein-Uhlenbeck generator. Now, Ornstein-Uhlenbeck process is diagonalized. The generator is diagonalized by Hermite polynomials. It's the quadratic oscillator, harmonic oscillator. Turns out actually that this generator is diagonalized by a similar family, but a Q generalization of the Hermite polynomials. And using this, we're able to prove this sort of identity. So let me introduce to you what is called the Q inverse continuous Hermite polynomials, orthogonal polynomials. So these are denoted Hn, and they depend on x and q, and from 0 to infinity. So they're defined recursively, so h minus 1, which isn't actually in the family, is just set to be 0. h0 is 1. And then sequentially you define them in the following way. You say 2x times hn, maybe I'll suppress the argument, is equal to hn plus 1 plus q to the minus n minus 1, hn minus 1. If you replace this just by n, this is the Hermite polynomial. Okay? So this is the deformation of this. And, you know, okay, so these are these polynomials. Now, in order to use them, we want to somehow relate them to the, to the eigenfunctions of k. So we actually need to filter them through this same quadratic map f alpha. So I'll define kind of an auxiliary set of functions. I'll call them hn tilde. And these are going to be equal to hn evaluated at f alpha of s, q. So what this means is I have my polynomials, and now I map an integer value through this quadratic function, and now I consider them as a function of s. So then the statement is, let's see, then k, this very simple generator, is diagonalized by these hn tildes with the eigenvalue q to the n over 2. And moreover, in fact, the hn tildes are orthogonal relative to the following inner product. So let's say for a and b being equal to 0, we have the following identity. So if I take a sum over all spatial variables s of h a tilde s, h b tilde s, and then I hit it against a weight function ms, I'll tell you in a moment, then this is 0 unless a equals b, in which case it evaluates to some simple multiplicative term. Okay, and the m is the following weight function. So it depends on alpha and q. And then there's some normalization, some minus alpha. So just constants that make this sum to 1. Okay, so these are orthogonal polynomials with respect to this. This ms is sometimes called a Q Gaussian distribution. And it comes up in the context of some problems in free probability as well. Okay. Now, there's a special case. If you take a equals b equals 1, I suppose, or 0, 0, then this shows that the sum of ms is equal to 1. And actually, ms is also positive. So ms is a probability distribution. Okay. So just like the usual Hermite polynomials paired up against the Gaussian distribution sums to an indicator function, so too is it with these Q continuous Hermite polynomials. So using the combination of this fact and the diagonalization, you can prove this evaluation formula, but you can also use this observation to define a stationary initial data for dynamic ASEP, because you see that the ground state of this is going to be related to this probability distribution. So if you take your half stationary initial data and you start to translate yourself far to the left, what will happen is you'll equilibrate to the distribution up to some periodicity by 2 given by ms. And so what the stationary distribution is, it's actually doubly stationary in space and in time. It says that you should let the probability of, say, m let's see, of S at any even location, so some, say, fixed even location, 0 for instance, the probability that that's equal to some height 2s, you call that ms, and then use the K Markov chain to fill everyone else in, to choose all other Sx. Okay, so what's happening is you basically, you fix the value at some point, say the origin, according to this ms distribution. There's some periodicity, so you need to fix it to be an even value. And then everywhere to the left, you choose according to your K Markov chain. And since this is true for any even location, you could shift this off to infinity and you get a stationary process. Okay. So this stationary initial data is stationary in two senses. It's stationary under x goes to 2x, to x plus 2. So under any sort of horizontal shift of period 2. But it's also stationary in time. So and under the dynamics of dynamic ASEP. Proving this is not hard. Once you observe that this, once you guess that this is the right stationary initial data, it's very simple. It's just detailed balance to confirm that this is true. Okay. I should tell you very briefly, where did this initial data come from, either of these? If you take the wedge initial data and you imagine running it for a while, it will also equilibrate. But it's kind of restricted by being started in a wedge. So it will kind of equilibrate at this log base q of alpha, but then everywhere else it'll kind of still be wedge-like. So you'll have this sort of roughly equilibrated picture and then wedge. But now you can raise the value of log base q of alpha high, and you can recenter yourself by where you would expect. And so from these wedge formula, actually from this formula in the duality, you can compute the moments of the one-point distribution, or even joint moments, and you get formulas. And it turns out that the formulas that are the moments of these sort of q expectations are exactly the moment problem. They correspond to a known moment problem for this distribution. So from that you can guess what the one-point distribution is, and you can go through and prove this stationary result. Okay, so let's see. So let's proceed now to using this information that we've gained, in particular the knowledge of the stationary measure, and I don't claim this is the only stationary measure, but I think it probably is, as well as the duality. So how can we use this to start to infer something about the scaling behavior? Okay, so a natural question is, under what scaling limits does the dynamic ASEP have an SPDE, or some sort of continuum limit? So one thing that you can start to do with that in mind is look at the stationary initial data. Under what scaling does the stationary initial data have a non-trivial limit? Okay. So the function ms, which is this discrete, or this q Gaussian distribution, the term that really matters in it is the q to the quadratic term. So what we're going to do is we'll imagine that q is like e to the minus epsilon. And then for that probability distribution to have a limit, it basically forces us to choose s, which is of order epsilon to the minus a half. Right? Because when you square that term, then you get the q to the s squared type term becomes a Gaussian factor. Okay. So that kind of fixes one scale. Now, if you look at the generator of this sort of stationary trajectory, this initial data trajectory, you need to ask under the same scalings, and again, everything is kind of centering by log base q of alpha, so alpha is unimportant. How does this rescale? And you see it rescales through an Ornstein-Uhlenbeck process, but in order to have that, you need to choose x to be of order epsilon to the minus 1. Okay, so at this point, you've kind of fixed all the scales but time. And it's not immediately obvious what the time scale is, but it turns out that the relevant time scale is going to be of order epsilon to the minus 2. Okay. So let me state a result now. So this was the first part. We're kind of transitioning now to the second part.
Sorry, so
Yep.
there is a unique invariance measure.
Well, I didn't say that. Maybe there is.
So would that mean that S odd would have the same law as S even?
No. So S odd, by parity, it needs to be different. And so what happens is you can write down what S odd is, and it's basically the same type of marginal MS, but where the values of alpha in this formula are shifted by Q alpha. So you can also write down, given the value on the evens, what's the value on the odd, and it takes the same form up to some simple change of variables. Yeah. Okay, so under this scaling, there'll be a limit. Let me write down to the sort of prototype. So there are two ornithine processes in the picture. One is the sort of stationary initial data that we see, right? So under this scaling, the stationary initial data becomes a spatial Ornstein-Uhlenbeck, but then there's also a space-time Ornstein-Uhlenbeck process, which preserves one-dimensional Ornstein-Uhlenbeck initial data. And I'll just write a kind of generic one. And it will be convenient, actually, even to put in some time-dependent term in front of the noise. Okay, so that's time. Okay, so the theorem says that we apply the scalings above, and then we set H epsilon, well, as one should according to this. So we're going to take the height function, run it to time epsilon to minus 2t, space minus epsilon to minus 1x, subtract off the sort of log base q of alpha, and rescale the whole thing down. And assuming that the initial data converges, so assuming H epsilon at time 0 has some nice limit and some moment growth conditions, then the same is true for all time. With the value of A here equaled minus a quarter, and the value of B just identically 1. So what's happening is under this scaling, the only remnant of the dynamic parameter, the dynamic, the reversion, is the fact that you have this Ornstein-Uhlenbeck term here. Okay. Now, how does this compare to, say, results just for standard ASEP, right? So this is what I would call a very weak asymmetry result. I might call it a very weak result, but then I would be doing myself a disservice. So very weak. What this means is that the asymmetry is of order epsilon, and then I'm applying this sort of 4-to-1 scaling. If I remove the very weak, and I just wrote weak, then I would have in mind an asymmetry of epsilon to the 1/2, which is like what Bertini and Jacquemin have, and you have KPZ scaling limit. So under the very weak asymmetry for standard ASEP, not for the mean reversion model, it was proved in '89 by Damasi, Prasuti, and Sacchiatelli that the height function, so if you do the same scaling and same, you need to center now by the hydrodynamic equation, but that it would converge just to the additive stochastic heat equation. So A would be equal to 0. Yeah, so the only difference here is the presence of the mean reversion term. Now, I thought for a little while, maybe you can just kind of couple together a bunch of their results and prove this kind of in a very soft way. I don't think it's the case, but it would be nice if it was. So what I'll do is I'll explain to you our approach. And actually, our approach is more similar to a work that came 2 years later of Dietrich and Gardner. So they proved the sort of same result as in '89. So the work in '89 went through correlation functions. You look at the correlation functions for this very weakly asymmetric process. You derive a complicated set of equations that they satisfy. It doesn't close, but then you use the duality for the symmetric model to kind of show that even though it doesn't close, you can get a pretty good approximation for the behavior of these correlation functions. What Dietrich and Gardner did is they used Gardner's microscopic optical transform, which actually transformed the asymmetric simple exclusion process into a microscopic stochastic heat type equation, and then they used the analysis of that directly. So what we're going to do is we're going to apply some sort of discrete optical transform or discrete Gardner transform, and in order to guess what it is, we'll use the duality. Because the duality tells us, we'll only use the one particle duality. If you want to see the use of one and two particle dualities for stochastic PDE limits, Hao will talk about that in his talk a little later in the week. So we're going to look at the one particle duality, and actually we're going to kind of shave off everything that doesn't really depend on S. And the only thing that really depends on S is this F alpha term. So let's define, so here's kind of a proposition that goes into the proof. So we'll define some Z alpha, or some Z tilde, to be just this quadratic function along the trajectory of dynamic ASEP. Okay, so I take my F alpha, which I remind you is written up here. I apply it to Sx of t, and then just for simplification, I put in some time factor in front. That doesn't really matter. And the claim is that this solves a simple equation that dz tilde is root q discrete Laplacian z tilde dt plus a martingale. So somehow this f function has simplified the evolution. It's turned it into a stochastic heat equation. And you see, why is this true? Well, if you took the expected value, it kills the martingale. That's just the duality, the one particle duality. And so because you didn't take the expected value, you have a martingale left in the picture. And so the whole game becomes to figure out now the behavior of this equation. But everything's explicit and it's kind of linearized and everything. So there's another theorem which ultimately proves this, which says that this z tilde. So let me define an epsilon rescaling of it, and actually it's the scaling in epsilon in front is the opposite, and then I do the same time scaling. And then the claim is that this actually goes to just a standard, well, it goes to the Ornstein-Uhlenbeck, but with a set equal to 0, and b of t equals to t over e to the t over 4. So that kind of seems a little annoying, right? Because here we wanted to get an equation with mean reversion, but clearly there's no mean reversion in this discretized picture. But if you do some Taylor approximation, you see that this is equal to t over 4 times the height function that we're interested in. And so just through change of variable, this tells us that this height function h epsilon is converging to what it should converge to. So everything really just goes into proving this result. Okay. And the machinery of that is through the martingale problem. And even though you're proving a convergence to a fairly simple object, it turns out you need to use basically the same strength of what Bertini and Giacomin use on controlling the sort of quadratic variation term. You really need to control terms like discrete derivative in the plus and minus direction of the heights. So you have these sort of terms, and you need to control their behavior effectively. Okay, so so this is the sort of result, but it's just for this very particular type of dynamic. And of course, you expect a much more general result should hold, and so this can also be proved. The approach that we use on the line is not so well adapted to doing kind of more general types of dynamics. This is the downfall of this microscopic optical transform, is that when it works very well, but it doesn't always work. So there are examples where it works and it kind of breaks a wall. So the stuff Hal will talk about, showing something like this stochastic 6-vertex model goes to the KPZ equation. Right now it's the only way we know how to do it. There are other models where you have some inhomogeneities in ASEP where you can really use this effectively. Ultimately, I think this approach needs to, this microscopic Hopf-Kohl gets replaced by something stronger. But, nevertheless, one wants to do it. And the hope is that actually with more of an analysis, one can prove convergence to some sort of generalized KPZ equation. Before I talk about the torus, let me explain why that might not be so simple. If you look at the stationary initial data and you try to apply just the weak asymmetry scaling, then you would find that things kind of don't match up right? Because under weak asymmetry, just weak asymmetry would have e to the minus epsilon to the 1/2, and the same scaling of space and time and everything else. But under that, the discrete, this Q Gaussian distribution just converges to 0, a 0 delta mass. And the Ornstein-Uhlenbeck also converges to just a constant function. So what it's kind of telling you is that under this under the weak asymmetry, the stationary measure is 0. And maybe that's not wrong, because what happens is, KPZ has some overall drift, rather fast drift. And so I think what will happen is if you start above your sort of equilibrium height, you'll just be KPZ, and then you'll die. And if you start below, you'll be KPZ, and then you'll, depending on the sign, you'll die. So the interesting thing to do, which is something that we have in mind to do next, is to actually tune the value of alpha kind of simultaneously with time. And in so doing, you probably can focus yourself in the right vicinity. But when you do that, you lose the duality. So, well, the duality depends on the particular value of alpha. Now, you could kind of simultaneously use different dualities for each time. That might work.
But you could already get something interesting with just taking alpha to be some power of epsilon. Take the prime power of epsilon.
That's possible. Maybe, or e to the power of epsilon or something like that.
Well, epsilon is something. You want it small. You want it away from 0.
I'm not sure, because the value of alpha just changes your centering.
Yeah, that's what you want.
But you want to, I think you want to change it kind of with time.
Because you want to put yourself in the regime where you start to see the KPZ sort of slowing down, right? The KPZ sort of falls down, and at some point it gets slowed down, right? So there might be a regime somewhere.
No, but I think if you set alpha to be a particular, some function of epsilon, it sets, that here's the base, right? Now you need to decide where you start. So either you start at
order 1.
You start at order 1, then I think what will happen is it will just immediately flatten out to 0. I could be wrong. But okay, maybe not, Because why does it matter what value you set alpha to? All you do is change your variables, right? You just subtract off that log base Q of alpha.
It does matter if the time it takes you to move by about that value is much longer than the time you consider.
Right, so but that would mean that you start kind of, so you can also think of alpha as fixed and change your initial data, right? So, you move your initial data up high enough, so it will kind of decay linearly, and then once it gets down to this value, it will just stick to it. I don't know, this is...
At times you'd move it further up than epsilon to the -2.
But then you might just see KPZ the whole time. You might just always see KPZ and never go to 0.
Might not.
There'll be an intermediate time when you see the things slowing down.
Maybe. I'm not sure. Anyway, so I think that's a good question. And really, if one can then tune the behavior to get some sort of nonlinearity going on here, showing the crossover behavior, I think for that you would actually need to tune the value of alpha, as a function of t, because otherwise it seems like you'll kind of just hit it and then stick at some point. Okay, so there's also a sort of analogous result in the context of the torus, where we can deal with a more general type of dynamic. Basically, you can replace, rather than having just this linear function, you can you can say get rid of the value of alpha. Alpha is kind of unimportant. And you can replace this just by some function, f of s, maybe minus f of s. Okay, some function of s. Now, when you're on the torus, it's convenient to assume, say, a half filling fraction, just so that you have the height function wrapping around. If you're not, you need to introduce some drift or some sort of tilting. And then the result that we have right now says that as long as this function f behaves roughly linearly, then on the torus, you'll also, under the same scaling, you'll converge to the Ornstein Uhlenbeck, but on the torus with the value of b equal 1 and the value of a also equal to minus a quarter. That result doesn't use the duality. It uses the sort of de Prato-Debouche method. You basically linearize the microscopic equation and then control the behavior of what's left over using properties of the linearized equation. So, okay, I want to close just by giving you already I mentioned this question of understanding generalized KPZ. I think this is something that would be interesting. Another question is to understand the hydrodynamic limit of this model. Because you do, when you're above this equilibrium height, you behave like, say if you're under hyperbolic scaling, you would behave just like the Burger's equation going down. And if you're below, you behave like the Burger's equation going up, right? Because there's this sort of sign change between 1 over 1 and q and 1. And so somewhere the two need to get stitched together. And it's possible that they just kind of get very naively stitched together and they kind of just stick to the height 0. But it's also possible that something more non-trivial happens. If you have kind of sinusoidal type behaviors, that there's some effect of what's above 0 and what's below 0. So I think it would be interesting to figure out that as well. Okay, I think I'll stop here. Thank you.
Questions? No? Ivan, I have one. If you look at the density of particles, do you know what are the fluctuations? What would be the SPDEs?
Well, I would imagine you differentiate, and that would give it to you. I'm not sure. The only issue is, somehow because there's this height dependence in it, it's a little bit more complicated, right? Because it's not enough to just know the local density, right? If you need to know the height. That's why you can't think of it as a particle process, unless you kind of keep track of like a gauge of the height at 0 or something of this sort. So it's, maybe it's, I'm not sure that's the right way to think about it in terms of the density. Anytime that you have this height dependence on it, you can't really differentiate.
Any other questions? No?
You disagree.
No? Okay, so let's thank all the speakers of the afternoon.